So last time we looked at how we can come up with the instantaneous rate of change by looking at something called the derivative or the slope of the tangent line, which was really taking the limit as, scroll back up here, the limit as x approaches 4 of, again, in this example, of the f of x minus the f of 4 over x minus 4. So what are we really doing? We're taking, on a graph, we're taking the average rate of change and letting that x get closer and closer to c, which is the point that we're interested in the instantaneous rate of change. So the average rate of change is the slope of this secant line that we start with. That's the average rate of change. And then when we take the limit as x approaches c, we get to the instantaneous rate of change. So what we want to do now is do that in an application problem. So what I'd like you to think about is if I said to you, suppose that you are driving in your car and your speedometer is broke. So you can't see what your speed or your velocity. So velocity is just speed with a sign associated with it, signed positive or negative. And in an example like what we're going to be talking about here, rectilinear motion, positive direction would be moving in a line, that's rectilinear motion, to the right, and then negative would be moving to the left. When we get to the height examples, like of a ball thrown in the air, positive velocity, you're on your way up, negative velocity, you're on your way down. But essentially, speed and velocity, speed is the absolute value of velocity. So suppose you're in your car and your speedometer isn't working and you wanted to come up though with an idea of how fast you were going. Well, one thing you could do is you could maybe use your odometer to see how far you traveled over a certain amount of time. And then you could use your change in distance over change in time. That would be your average speed or your average velocity over a certain interval of time. Well, then how could you get a better estimate for that? Well, you wouldn't wait an hour later, you wouldn't wait a half hour later. You would let that second, that second point that you were looking at later down the road, you would let that get closer and closer and closer to your initial point that you were interested in knowing your speed. And so letting that elapsed time in between when you start and then when you kind of look at what's my distance at this point, that change in time, you would let that change in time get smaller and smaller and smaller. So we then say, let's take the limit as the change in time interval goes to 0. And that's essentially what we're talking about here. So on the left, we have our average velocity. Our average rate of change is simply change in position over change in time. So this is just a specific example of average rate of change. Now, if we were to let that change in time go to 0, like what I was just mentioning, then that's letting that, as you see on the right-hand side over here, that's letting that delta t go to 0. So letting this change in time here, letting delta t go to 0. And then that's going to be equivalent to saying, okay, let's let that second point in time get closer and closer and closer to that initial point in time at t sub 0 when I first maybe was interested in knowing what my speed was at that instant. And so now we're really just looking at a derivative. Okay, so the instantaneous velocity, the rate of change at an instant, that's the derivative, versus the average rate of change or the average velocity over an interval. So exactly what we were talking about last time, but put into the context of a very common application that we're going to see. So let's look at this example. So an object moves in what we call rectilinear motion, so it's motion in a line, according to S of t equals 12t squared plus t centimeters at t seconds. So that's the distance that it has traveled, S of t, at t seconds. We want to approximate the velocity, so approximating the velocity, so that's average velocity, but we're going to approximate the velocity at 3 seconds, so that's really the point of interest of the problem, what we would have called c, maybe in the last set of examples we did. And so in this case, this is our t sub 0. And we're going to let our change in t be 1/10 of a second, 1/100th of a second, and 1,000th of a second. So let's get to it here. All right. So first of all, when you see this approximate the velocity, so as soon as you see that, I want you to be thinking, okay, this is my average rate of change. So when we see approximate the velocity, this is really saying it's this average velocity that we're talking about. And so our average velocity, that's really the box that you see up above on your left. That is simply your change in position over your change in time. All right, and now we're going to do this for 3 different intervals of time. All right, so let's see what we can do here. So the first one we want to look at, so we have 3 different values we're going to look at here. So we're going to do this for when our change in time is equal to 1/10 of a second, obviously, is what we're talking about here. So I'm just going to actually put that kind of thinking here in parentheses. All right, so what does this mean? So now I need to do what my position is after, so I'm going to be doing my S of 3.1, because remember we're starting at 3. So actually let's write something out. This change in time being 1/10 of a second, that is the same thing as saying on the interval from 3 to 3.1 seconds. Okay, those are synonymous. All right, so we would be doing S of 3.1 minus F of 3, S of 3, all divided by 3.1 minus 3. Okay, then when we look at, so let's just kind of set all these up here. Then I'm going to change that from 1/10 to 1/100th. And again, that's going to be the same thing as saying on the interval from 3 seconds to 3.01 seconds. So this is going to be looking at, again, the change in the position. So S of 3.01 minus S of 3 divided by our change in time. And then the last one here is going to be looking for when our change in time is 1,000th of a second. And so again, this is the same thing as saying from 3 to 3.001. And so this is going to be the position at 3.001 seconds minus the position at 3 seconds, and then divided by that change in time. All right, so I did not mean to erase that whole thing. I was just going to clean up that little piece here. All right, so this was, my first was change in t was 1/10 of a second. All right, so now my S of 3.1, so if you were to sub, and I'm not going to show all the work all the time here, but if you were to sub your, 3.1 seconds back into the original function, so this is S of 3.1 minus S of 3, of course, is subbing 3 into the original position function here. And so if you were to do that, this would have come out to be 118.42 minus, and then this comes out to be 111. And then that whole quantity there gets divided by 1/10. And so we end up with 7.42 divided by 1/10. And this is then 74.2. And thinking about our units, it's a velocity. The change in position in this case was in terms of centimeters per, the change in time was in seconds. So my average velocity from 3 seconds to 3.1 seconds, I averaged a velocity of about 74.2 centimeters per second. And so on. The rest of these would follow in a really similar way. I'm just going to kind of take us right to the answers here. So this one comes out to be about 73.12. So this is just calculator work here. And this comes out to be 73.012 centimeters per second. All right. So as we look at this, we should be able to kind of observe as we look at these values that we're letting that change in time get smaller and smaller and smaller, or we're letting that second t point, let's say, get closer and closer and closer to t sub 0, or what we used to call c, get closer and closer to 3. And so if I was to make a hypothesis at this point, so if I was to look at these values, 74.2, 73.12, 73.012, I might make an observation, kind of based on these values. So let's just kind of say here that it somewhat looks like, and we'll see if that's true, looks like maybe the instantaneous velocity. So the velocity right at 3 seconds. So it looks like the instantaneous velocity at 3 seconds. Looks like maybe that's approaching 73. So it kind of looks like these values are getting closer and closer to 73. So we don't really know yet for sure, but that's what we're going to investigate here in part B. So part B, now I want us to do just that. So for part B, we are going to find, a little sloppy there, just what I said there. So we're going to find the instantaneous, so instantaneous velocity. And honestly, I wouldn't have to say instantaneous. If I just say find the velocity at 3 seconds, that implies the instantaneous velocity. So in some ways, I could even maybe kind of think about putting that in parentheses. So when we say find the velocity at 3 seconds, that's what we mean, instantaneous velocity. All right, so instantaneous velocity, let's go up and kind of take a look at my boxes here. So that's the second box on the right. So that's the instantaneous velocity. So what are we doing? Now we're, instead of just looking at these intervals getting smaller and smaller and smaller and observing the numerical values, which is what we were doing, we were looking at, taking 74.2 when the change in t was 1/10, and then going to 73.12 when the change in t was 100th, and then we ended at 73.012 when the change in t was 1,000th. So now we're actually going to let the limit as that change in t goes to 0, or let the limit of this t get closer and closer to 3. So instead of 3.1, 3.01, 3.001, let's let that t go to 3, because that's what we're doing here numerically. All right, so that's exactly what we're going to do here. So now we're going to take our limits as t goes to 3. So let's just kind of pause here for a second and observe something. So the t that's going to 3 is this t right here, 3.1, 3.01, 3.001. That is the t that's getting closer and closer to 3 each time. So now we're going to use our limit to actually find what is it actually going to. And then it's the, just like yesterday, whatever, this is the same day in my world, and probably is in yours too. So in the last video, I meant to say, it was the s of t function. So that original function in this case is the 12t squared plus t minus, and then it's the S of 3. Well, we computed S of 3 up above here already, and we saw that that was 111. So I'll go ahead and write it out though, just so maybe if you're looking back in your notes, you'll see where it came from. So this was actually subbing in the 3, so that's our 111, all divided by our t minus 3. Okay, so we have limit as t goes to 3, 12t squared plus t minus 111. So limits, the first thing I do is I try my direct substitution. Of course, the problem is in this case, if I do that, I am going to get that old 0 over 0 problem of an indeterminate form. So here's what we do with these 0 over 0s. When you have all these polynomials here, it kind of calls out with these rational functions to factor and reduce. And so I'm going to factor this, and I'm going to factor by cheating, is what I'm going to call it. Because here's the thing. If I need to reduce, what I'm going to ultimately, hopefully be able to reduce is going to be a t minus 3 over itself, right? T is going to 3. The only thing in the denominator is t minus 3. That's what's going to 0. So there will likely be a t minus 3 factor in the numerator that will reduce. So I'm doing my trial and error technique is what actually it is, but it's kind of with this forethought in mind of where I think I'm going with this. So now thinking about, t times 12t gets me back to my 12t squared term, the first term. And then kind of off to the side in our calculator, we'd have to do 111 divided by 3 to figure out in order to get to the last term, that's actually, that's actually 37, right? And now let's just get our signs right. Right now I have a minus 36t, kind of from those outer terms. I ultimately have to get to a plus t in there, so that means this is going to need to be a plus 37t. So it's factoring with trial and error, but it's made easier by kind of knowing where this thing is likely headed. So here I am able to reduce away, changing the function slightly, but the limits are still equal there. So now, after I do that, I now have my limit. So here's where we are. We have our limit as t goes to 3 of just the 12t plus 37. And now, of course, we can evaluate this subbing in our 3. So 12 times 3 plus 37. So that's our 36 plus 37. And so that's going to end up giving us our 73, just like we hypothesized. 73 centimeters per second is our instantaneous velocity, our velocity right at 3 seconds. All right, so the last thing I want to do in this video is I'd like to just show you when you're using your calculator up here in part A, rather than kind of like type these things in repeatedly, whenever you're using the same function over and over, it's a good idea just to store it in Y1, and then your calculator recognizes function notation. So suppose I have, let's bring up our, let's try this again. Let's bring up my calculator here. And so in my y equals, I've already put in our s of t function. So there it is, 12x squared plus x. So here's what I would do. I just want to show you this feature. So let's go back to the main menu. So second, quit. And again, this is an app that I have, and so the interface looks the same. Sometimes the displays are a little different, and it has some limited functionality. So when you hit certain menus on your graphing calculator, you're going to see more options. But what we're going to start with is we're going to hit the vars menu, which is variables. And right now it just says quit. It's weird. But when you hit it on your calculator, you're going to see a whole slew of options, none of which we want. We want to arrow to the right to y variables. So you hit vars and then arrow to the right to y variables. And again, on your calculator, you're going to see more options. This one just has the one and only function I want, which is number 1 function. And then you're going to have this full list of different functions that could be stored in your calculator. Mine is stored in y1, so 1 for y1. So guess what? Your calculator recognizes function notation. You can do y1 left parenthesis of, like f of 3.1, right parenthesis close. And obviously that would give you your 118.2. But you could do this all in one fell swoop if you wanted to. You could do variables, y variables, function y1. You could do y1 of 3.1 parenthesis minus variables, arrow to the right to y variables, enter on function, enter on y1 of, with parenthesis 3, close parenthesis, and that would be my 7.42. That was our numerator in the first step, and then of course the denominator, that was pretty easy, that was just our 1/10. And so there's my 74.2. So again, we could do the same thing again here. We could do variables, y variables, arrow to the right, 1 on function, 1 on y1 of, parenthesis, 3.01, close parenthesis, minus variables, arrow to the right for y variables, 1 on function, 1 on y1. I know that seems like a lot, but it's one of those things that once you kind of go through that sequence a few times, it will become much quicker, trust me, much quicker than typing this in every time. So what you don't want to have to go is go, okay, well, what is 12 times 3.001, that's raised to the, I guess that was the second power, and then it was, what's the next part of my function? Plus that same value, 3.0. Every time you do that, you're just going to increase the likelihood that you make a data entry mistake anyway. So store it in your y1 once, and then you can use this variables, y variables, function y1 sequence, and it will recognize that function notation. So just a little piece of advice in terms of working with your calculator. And so that's it for this one.